Hello scholars, welcome to Oceanography. Today we are discussing Chapter 8, all about waves, all about water dynamics, all about what propagates through the ocean in the form of waves. So let's get right into it. Today's lecture, talking about where do waves come from? The wind. What causes them? Storms. What are waves actually doing? They're transmitting energy across the ocean surface. What types of waves are there in the deep water, in surf zones, and what are their characteristics? And then we'll dive into a big discussion on what are tsunamis and what do they do. So, wave generation requires a disturbing force. So waves aren't created out of nothing, out of thin air. There's actually a force over an area that causes energy to move. And wind blowing across the ocean surface is that disturbing force. Now, as we know, the Coriolis effect creates circulation patterns. There's 3 convection cells, Hadley-Farrell polar, and it gives us the trade winds that blow to the east, the westerlies, and the polar easterlies. These winds have friction on the surface of the ocean, and that is the disturbing force, the wind-generated waves, ultimately coming from the rotation of the Earth and the sun. So we're back to our friend the Coriolis effect. We're back to our friend the spinning of the Earth on an axis, and of course our friend the sun. At the interface of fluids of different densities, waves are generated. So we have air-ocean interface creating ocean waves. We have air-air interface creating atmospheric waves, and then a water-water interface creating internal waves. And this happens at the pycnocline, where you have an increase in density from the surface layer, the surface mix layer, pycnocline, we're talking about the layers of the ocean, into the deep ocean. Now, the differing densities of the surface layer and the deep layer actually create internal waves at that interface. These waves are larger than surface waves. They're deeper than surface waves. They're caused by tides, turbidity currents, winds, and ships, and they are hazardous for submarines, where, as we will see, surface waves don't go that deep into the oceans. They reside only in that surface mixed layer. So what are waves doing? Waves are transmitting energy. And the energy travels in a wave. The ocean particles, the molecules, actually end up in the cyclic pattern where the particle moves up and down, back and forth, around and around. We have 3 main types of waves: longitudinal, transverse, and orbital, and they have different characteristics. Longitudinal waves are the push-pull. This is the same as, if we were to think about seismicity, this is the same as the primary wave. So it's a push and pull, a compression and release, and the energy is in a forward and back movement. Energy like this can move through solids, liquids, or gases. We have transverse waves. Transverse waves are going to be the up and down motion. It's kind of like when you have a hose and it's stuck. It has a little bend, a little bind in it, and you pick it up and you try and shake it, and a wave moves down. Well, this is our transverse wave, also called side to side. The energy moves at a right angle to the direction of the movement, direction of the wave, up and down at that right angle. These generally only move through solids and not liquids. And then we have orbital waves. These are the cyclic motion, and it goes down into the water column, and it gets smaller and smaller and smaller, and it diminishes the deeper that you go. And the particle actually moves in this circular fashion. This is how waves are on the ocean surface. So there's a lot to waves, a lot of different characteristics, and it'll be important to understand these different components of a wave to understand the features of how the waves function. So some big ones are the crest and the trough. The crest is going to be the top of the wave, and the trough is the bottom of the wave. We can see it here. The crest is the top of the wave, and the trough is the bottom of the wave. The still water level is going to be the space right in between. So as you have this wave kind of like this, we've got a crest and a trough. The still water level is, if those two canceled out, it would be the median right in between the two. The difference between the crest and the trough is the wave height. The distance between one wave crest to another wave crest is the wavelength. And then the very, very bottom of where these cyclical waves connect to is going to be the wave base. Now that we know all these different terms, we can start to understand what's going on with these waves. So waves travel, zoom, zoom, zoom. And we talked about the wavelength being from one crest to the other. So if we look at a point, and the time it takes to move from one crest to that other crest is going to be the period. Now, the period is a fixed point. So we could say if this is our point right here, how long does it take for one wavelength, boom, to pass it? Frequency is going to be 1 over the period. So when we're thinking about frequency, we could think how many waves per minute, how many waves per hour, how many, and so it's going to be 1 over the period, or the inverse. Waves have a steepness to them, and that steepness is wave height over wave length. And this is important because if the wave steepness is greater than 1 over 7, then the wave breaks and it crashes. But if it's less than 1 over 7, then it stays in that wave form and you don't have any wave breaking. This circular orbital motion is important because it's the particles in the ocean moving in a circle as the waveform travels forward and the wave energy advances. So when waves are generated out at sea by a storm, they're not pushing water from the middle of the ocean all the way up to the coastlines. No, the energy of the wave is traveling through as the particles move in a circular motion. Here, this little ducky example shows that as the wave is moving from left to right, this wave moves through the duck. The duck moves up and backward, and then it moves up and forward, and then it moves down and forward, and then down and backward, forming a full circle as the wave travels through. Now, this circular orbital motion is the diameter of orbital motion that decreases with depth. And the wave base is the depth where orbital motion of the particle stops. And it is correlated to the wavelength. So we have a wavelength from one crest to the other crest, and then the wave base is 1/2 the wavelength, or you could say it's L over 2. Wavelength, wave base is going to be half as long or half as deep as the wavelength is long. Important because this helps us understand and classify different types of waves. So we have deep water waves. Deep water waves are when the water depth is greater than the wave base, greater than half the wavelength. And so this is the case for most waves out in the ocean. The wavelengths are nowhere near as long as the ocean is deep, so they're called deep water waves. Now, when we get closer to coastlines, the depth, as we know, we have the 3 marine provinces, the mid-ocean ridge, the deep ocean basin, continental margin. Closer we get, through to the continental margin, well, now the surface of the ocean floor starts to come up to intersect with land, and that ocean depth changes, which gives us different types of waves. They start to transition into surface waves. Now, it's important to know this because we can look at deep water waves and we can understand about how deep the orbital motion is going to be, and then use this information to create structures like floating runways, like wave power generators, or buoys in the ocean that we don't want to be affected by the deep water waves. We want the pylons, or whatever is connecting this, to be rooted deep enough so that the deep water waves don't affect it. And so here is the world's largest runway, floating runway in Japan. It has pontoons that are a base that are deeper than the deep water waves will actually be able to reach, thus keeping it relatively stable. Deep water waves are generated by the wind. And we have another concept, the wave speed, also known as celerity. And the speed is going to be the wavelength over the period. So you could think about speed as miles per hour. That's the common one, is we're driving around miles per hour. What is miles? It's a distance. Per hour, it's a time, right? It's a rate. So we could say wavelength is a distance over period, which is a time, or you could say this is in meters per second or in feet per second when we're thinking about how fast are these ocean waves going that are generated by the deep sea. And so the wavelength can actually tell us how long the period is and how fast the wave is moving, the wave celerity, which is pretty cool because if we can measure the wavelength of certain waves, then we can understand features and characteristics of these deep waves. For instance, a wavelength that is 100 meters long from crest to crest has a period of about 8 seconds. Now that is about 40 feet per second, roughly, or we could come over here and we could say it's about 12.5 meters per second. So we can understand how fast these waves are moving through the deep ocean because there's no interference of the ocean floor. They're just transferring energy through the surface layer of the ocean generated by wind. Pretty cool. When we get closer to the ocean, there is interference of the ocean floor, and so it changes things. These are called shallow water waves, where the water depth is less than 1/20 times the wavelength. Basically, this means that now the wave can feel the seafloor, and it changes the equations for how fast it's going. There's still characteristic speeds now that it feels the floor, but it changes into 3.13 times the square root of the depth, or for feet per second, 5.67 times the square root of the depth in feet. Wind can generate waves also in shallow nearby areas, and they have their own specific characteristics. These waves are the ones that break. These waves are the ones that people like to surf. They're the ones we go to the coast and we're like, those are cool. Look at these beautiful waves. Shallow water waves. Tsunamis also act like shallow water waves because they're so big, which we'll get into at the end. They're so big that they're a shallow water wave in the entire ocean. Tides are shallow water waves, and then particle motion is in a flat elliptical orbit. So it changes the shape of the wave as it's traveling through because of the action of the ocean floor. At some point between 1/2 wavelength, L/2, and 1/20 the wavelength is a transition, where the waves have characteristics of both deep water and shallow water. The celerity, or the wave speed, now depends on both the depth and the wavelength. And so this would make sense. Deep in the ocean, these waves are just cruising along, and then they get closer to the continental margin, and they start to have characteristics of deep water waves, but they're also starting to feel the ocean floor. And then when they get closer, they actually start to shift how they function, and now they're completely shallow water waves, and they have different characteristics because they completely feel they are integrated with what's happening on the ocean floor. If we think about beginning, movement, and ends, wind generates stress on the sea surface, and this stress creates what is called capillary waves. They're V-shaped troughs, they're short wavelengths, and then as these start to accumulate over a distance and over time, they turn into gravity waves, where we have an increase of wave energy, pointed crests, rounded troughs, wavelengths that are bigger than 1.74, and then as these waves get closer, the waves will begin to break when the wave steepness is greater than 1/7. The wave height over the wavelength is greater than 1/7. And so this gives us different properties to what the waves are doing at sea. What is the sea? The sea is where wind drives waves, and it is also called the sea area. So if we look here at the ocean, middle of the ocean, there's an area now. Then this is different than the 7 seas that we talked about, the Red Sea, the Black Sea, the Caspian Sea. Those are transitional areas from ocean to land that have salt water in them. This is sea. We could think of it as the sea area. The sea area is where waves are created. Deep out in the ocean, there's storms, there's winds. The storms are acting on this area and creating waves. Some important components that create waves is how fast is the wind blowing? How long does the wind blow? What is the area over which the storm is affecting? And the area is going to be known as the fetch, the distance over which the wind blows. Now, these three things together create different size of waves. Waves transmit energy through the ocean, and it can create different things. Based on these three factors, waves will get to a certain height. And the wave height is directly related to the wave energy, and the energy depends on the speed of the wind, the duration of the wind, and the fetch of the wind. Most wave heights are usually less than 2 meters. Breakers will have white caps when wave reaches a critical steepness, which we know is greater than 1/7. And there's this scale, the Beaufort wind scale, which looks at wind speeds and photos of what they look like. So it's observational of, given this wind speed, and these are the type of waves that we see. And it goes from 0 to 12, 0 being calm, 12 being hurricane, 12 devouring ships and breaking them down, 1 and 2 being light air, light breeze, pretty easy, and then everything in between. So it's important to classify and understand. It's kind of our thing that we do in science. We like to label and identify and communicate about how things are. So Beaufort wind scale gives us the ability to communicate about different waves that we see, but it's also quantitative based on wind speed. We can look at wind speed and wave height generation globally from satellites, and what we see is that the largest wave heights occur down here in the southern hemisphere. In the northern hemisphere too, these are around the tropics, and this is overlaps with the westerlies. The westerlies create some of the strongest winds in both the northern and the southern hemisphere. A little bit stronger in the southern hemisphere because there's much less land. Most of the land is in the northern hemisphere. And the Indian, Pacific, and Atlantic Ocean all combined to make a faux fifth ocean, the Southern Ocean. It's kind of its own ocean, but kind of not. It depends on what day we want to talk about it. There's also the Arctic Ocean. Southern Ocean is a combination of the Indian, the Pacific, and the Atlantic, and it creates some of the highest wave heights of anywhere in the world. So our understanding of oceans has come a long way. We still have a lot to learn. At some point, we thought maximum wave height, 60 feet. But then the U.S. Ramapo in 1933 was caught in a huge storm, and it made it. Amazingly, I'm not really sure how, because it's a giant ship and the waves are so big, 112 feet, and they measured these waves using simple geometry, and it blew that one right out of the water. Get it? But it was still in the water. And it showed us that, actually, waves can get really, really big at sea. And their specific properties, we might not know exactly what the upper limit of waves at sea are. In fact, there could be really big waves. So the U.S. Ramapo was undamaged. Other ships aren't so lucky. In fact, there's 100 to 1,000 ships that go missing every year due to these big storms. Here is an image of the aircraft carrier Bennington in 1945, where the front of it completely bent down. Boy, I can only imagine being on this ship during that period, during that storm, where the ship was actually bending. Wow, fearing for your life, but they made it. They made it through. Other ships, not so lucky. So wave energy transfers through the sea. Waves are created in the sea area. And then from there, they reach an equilibrium condition where the waves can grow no further, and then they travel. They travel outward through what are called swells, uniform, symmetrical waves that travel outward from the storm area. They have very long crests, and they move very long distances. Now, when these swells intersect with beaches, these are some of the waves that are really, really nice to serve because they change from deep water waves into transitional and then shallow water waves. We can look at certain conditions to develop swells in a sea. And it's going to depend on a variety of factors: the wind speed, the fetch, the duration, right? We talked about these three factors being important for developing waves. How fast is the wind blowing? How long is the wind blowing and over what area? And what we see is that it is an increasing amount of energy from increased wind speed. So from 20 to 40, waves go from about 10 to 40. From 40 to 80, waves go from about 40 to 160. So, whoa, okay. The more the wind blows, the more the waves get bigger. And so waves can just get bigger and bigger and bigger with increasing wind speed. So who knows? What is the upper echelon of wind that can blow? Have we ever seen it? Maybe, maybe not. Has anyone ever lived to tell about it? I don't know. Point being, there's still more to learn. You could take up an entire life's career in science and oceanography. Maybe you are the person who discovers how exactly large waves form, function, and what their limits are. Be a cool project. Swells are pretty cool. They have longer waves and they travel faster and outdistance other waves. They move in these wave trains where the first wave that's traveling will die out and a new wave will begin behind it, and that will happen over and over and over again. It's kind of a cool feature. So the entire swell transfers all this energy. The front wave loses energy, but a new wave behind creates more energy, and the whole thing travels about half the speed that a single wave would do. Waves like to travel in trains, or I should say, these swells. Waves from fully developed seas travel long distances in these wave trains, and the front dies out and new ones create in the back, and the overall wave train travels about half as fast as you would expect a single wave to travel. Now, waves interfere with each other. And when you have two waves in phase at the same time, what you get is a really big wave. They add. When you have two waves out of phase, they cancel each other, and you get no waves. So this is called constructive and destructive interference. And you could think about it like if you drop two rocks in water, still water, here and here, bloop, bloop, at the same time, they're both going to send out waves. And those waves are going to interact with each other. That interaction we would call interference. And when the wavelengths add in phase, it is constructive. And when they cancel, it is destructive. And what we usually get is this mixed interference for how the waves are actually acting. You get some high points, some low points, and then everywhere and in between. Now, it's important to isolate things to understand them, but we understand that these processes happen much more complex than just a single storm blowing out at sea. There's lots of storms. The ocean, when we look at the planet, wow, it's blue, but it's often covered in clouds, and there's storms everywhere. Multiple hurricanes out in the Atlantic happening at one time. How do those waves interact with each other? Well, they're going to act with mixed interference. Sometimes these interference patterns can cause a rogue wave. One massive, spontaneous, huge wave that can reach abnormal heights. And these waves are ship sinkers. You don't see them coming. You have no idea. They're also really, really hazardous for people on the beach. On the beach, they're called sneaker waves. You don't see them coming because you're just hanging out, having a great day, enjoying the sun, enjoying the surf, loving life, hanging at the beach, and then boom, a huge wave hits and it sweeps you out to sea, and next thing you know, it's game over. And unfortunately, I've tried and bring it a little bit light, but unfortunately, sneaker waves cause many fatalities every single year. The ocean is powerful and the ocean is dangerous, and these rogue waves are definitely something to be cautious and cognizant about, whether you're on a boat or you're at the beach. They're really hard to forecast. We don't know exactly where or when they're going to occur, but they come from strong ocean currents amplifying opposing swells. Kind of like the two rocks being dropped into the ponds, and it creates waves that go out. Well, if you have multiple storms happening, and it's sending swells out in all directions, and those swells interact with each other, one of those waves from one of those swells could create an enormous wave through the mixed interference of these different swells that are traveling through, and create a rogue wave. How and where those are going to happen, really, really hard to understand. Okay, so what happens when waves make their way all the way to the coast? Well, they enter what is the surf zone. Okay, so the surf zone is the zone of breaking waves near shore. We've got waves that start to shoal, and then we have waves that break and surf. It's when deep water waves encounter shoaling water less than half their wavelength. They become transitional waves, and then once they become transitional waves, they get close enough to where they become shallow water waves. And these shallow water waves are going to be the waves that create different types of surf. Same feature. When the wave steepness, the height over the length, is greater than or equal to 1/7, the wave breaks. As this wave approaches, the swells are coming in. Now, transitional, it becomes a shallow water wave. It feels the effects of the ocean floor. It changes the wave dynamics. The waves grow a little bit higher. The wavelength decreases. This changes the wave steepness, and at some point, the wave is going to break. This breaker in the surf zone is exactly what surfers ride on their surfboards. And there's 3 different types. There's spilling, plunging, and surfing. Spilling is when you have, and so these 3 different types are going to be based on the shape of the ocean floor right when the wave is breaking. Very gentle creates spilling breakers. The wave energy expends over a greater distance. The water slides down in front slope of the wave. Plunging breakers, these are going to be the type that create tubes that surfers can get in. These result from moderately steep. The wave energy is dispersed over a shorter area, and the wave crest starts to curl over. This is the best one. This is one that surfers love for. They're looking for these plunging breakers. Surging breakers, this is what body surfers, boogie boarders like to surf, because the ocean floor is so steep that the wave comes in and it breaks really fast, and it's going to break directly onto the shore. The energy is transferred in a very, very short distance. Surfing is cool. People have loved surfing oceans as long as they have lived on them. And the desire to surf the biggest wave has always been out there. And there are some huge waves. There's this surf break off the coast of Portugal that has massive waves, upwards of 100 feet. And surfers come out and they actually ride these things. They're towed in by a jet ski. They're holding on, they're towed in, and then the jet ski gets off out of the way, and then the surfer, it just surfs down and holds on, and these records are broken over and again because the hunt and the desire for the biggest wave is out there, especially in the surfing community. And so surfing is like being on a sled, but it's operated by gravity, and the surfboard displaces a small amount of water that creates buoyancy, and it keeps the person up, buoyant on the surfboard. But because of the angle and the shape of the wave, the surfer glides down the front, glides down the face of the wave, and understanding the mechanics, the physics of how waves are generated, how waves are transported, what happens to shallow water waves when they get close to the shore is all important for being able to surf. Whether you know as a surfer that's what you're doing or not, you have this very intuitive knowledge. So waves, now we understand a lot about waves. Waves do some really cool things when they get near the shore. If you've ever been to the beach, you've probably noticed that no matter where you are on the coast, it always seems like the waves are coming straight to you. But as we learned, the subtropical gyres are spinning in circles clockwise in the northern hemisphere, counterclockwise in the southern hemisphere. So think about California. If it's clockwise, then that means the longshore transport is actually from north to south, which means the direction of the Ekman transport of the water is away from the shore. What? But the waves are coming at me. What exactly is happening here? Well, waves refract. And this refraction is the bending of a wave as it approaches shore, because the wave speed is proportional to the depth of the water. And since there's differing depths when the wave is coming, it will actually slow down in shallower water relative to deeper water that's faster, and it will curl around. So no matter where you are on the beach, it feels like the waves are coming at you directly parallel. The wave energy is unevenly distributed on the shore, and it goes through these orthogonal lines that are perpendicular to the wave crests. There's more energy on headlands, the points that stick out, than there is in bays. And so wave refraction will cause erosion of the headlands and deposition in the bays and help to create coastal features, deposit beaches, erode and wither away headlands. And this all happens because of the transmitting of the energy of the waves that are created deep out at sea. So waves are just moving energy, and then they're helping to sort and create features on the coast. Here we can see a headland. The direction of energy is coming in. As we move around, these waves bend because of refraction. And again, no matter where you are always going to feel like the waves are coming directly at you, even though their original wave angle may not be in that direction. Here we can see the angle. If we kept this line here on the top going straight, it would intersect this bottom beach at about a 45-degree angle, but that's not the case because of wave refraction. Waves also reflect. And you could think about this if you have, if you're in the tub and you push water forward, the wave is going to go forward, and then it's going to hit the end of the tub, and then it's going to come back to you. And so waves do this also. They reflect off of different jetties, different features, and they can interfere with each other constructively, create bigger waves, and also be very dangerous based on what's happening and where this is happening. So waves do lots of really cool things when they get near the shore and they start to interact with coastal features, coastal topography. When two waves with the same wavelength are moving in opposite directions, you get what is a standing wave. And basically it's a wave that looks like it is flowing continuously. You see this on rivers when the water is moving over a big rock and then it looks like it's so smooth and moving. So this has been recreated in river parks and surf zones. So here you see all the little surfers just hanging out, and then there's a wave that you can cruise back and forth, and you can create the hydraulics. You can put boulders and create a very specific way that the water will flow over to create this standing wave. I'm going to skip that one and move straight into tsunamis. So tsunami is a Japanese word for harbor wave, and where Japan lies relative to the convergent boundary just offshore makes it very susceptible to a lot of tsunamis. And more commonly, these would be called seismic sea waves, where you have plate tectonics shifting at the bottom of the ocean, sending energy out that then moves very far distances. Now, these aren't the only ways. It's the most common, but underwater landslides, volcanoes, volcanic eruptions, even meteorites can come in and sploosh. Kind of like you drop rocks into the ponds. Well, the oceans are just a really big pond, and you would need a really big rock coming from the universe or from the solar system that can create a tsunami. So tsunamis are like surface water waves, but they expand the whole ocean because their wavelengths are super long. They can be greater than 125 miles. That's a long wavelength. As opposed to wind-generated wavelengths, capillary waves are really tiny. And then they get a little bit bigger. These ones are huge. And their speed is proportional to the water depth. So when it happens in deep ocean, they move super, super fast. They're very hazardous, very destructive because they're huge waves. And basically, a tsunami, the wavelength is so long that when it gets close to the ocean, they create these massive walls of water. And if it's a wave traveling, there's multiple wave crests. And so the wave comes in, and then you get a trough, and the water goes out. And then you get another massive wall of water come in, and then a trough, and it goes out. And another massive wall of water. And what they do is they flood and they inundate and they knock out all the different features, creating lots of different debris. And it's very, very bad if you live in one of these coastal communities, because the strength of the tsunamis, the energy that is being transmitted is immense. They're not something that we want to mess around with, and definitely not something you want to be hanging out with when a tsunami is happening. Most tsunamis happen around the Pacific Ocean, the Pacific Ring of Fire, the tectonically active region where there are lots of subduction zones and lots of associated seismic activity, lots of earthquakes happening in the Ring of Fire, and lots of coastline around the Pacific Ocean, lots of areas that are potentially in the direction of where tsunamis can hit. Hilo, Hawaii in 1946 got hit by a tsunami, causing $25 million worth of damage, 159 deaths. That's not, any death is tragic and is the loss of life. I feel that. 159 compared to the Indian Ocean tsunami, 300,000. That is an unreal figure. 300,000 people died in 2004 from the Indian Ocean tsunami. It was a huge mega thrust movement, magnitude 9.2 earthquake, and it sent a tsunami to Sumatra in like 15 minutes. And then it hit Sri Lanka, India, the east coast of Africa. It was massive. And unfortunately, back in 2004, there wasn't a good tsunami warning system. And so people, and just the education wasn't there, that be careful when the ocean goes out, because the part of a tsunami with huge wavelengths is that before the wall of water comes in, the trough comes in, and it pulls the actual ocean level way out, lower than low tide. So if you're on the coast and you think, hey, look, the heck is happening? The ocean's never been out that far. I'm going to go investigate. This is cool. Wow, I've never seen all this before. And then boom, the wall of water comes in. There's no chance. There's no chance for survival. So understanding how tsunamis work, hugely important. Japan, the Tohoku earthquake in 2011, magnitude 9.0, fifth biggest earthquake in the world, killed 20,000 people in Japan. Knocked out the 3 reactors in the Fukushima Daiichi power plants, leading to nuclear radioactive fallout. So the extent of the damage can be very, very significant. These are huge hazards. And when they kill a bunch of people, they turn into natural catastrophes. Krakatoa, the island of Krakatoa, basically blew up in 1883 from a huge volcanic eruption. The eruption was so big, it blew the island away. And part of that was a huge tsunami that was associated with it. So seismic activity is very, very integrated into, it is the root of most of these large tsunamis. The Indian Ocean tsunami we talked about, 1,200 kilometers of seafloor displaced, the deadliest tsunami in history, wiped out coastal areas. Shocking imagery that comes from it. Just coastal city. You can see high-rise buildings right here on the coast, and then a wall of water that is actually bigger than these high-rise buildings. It was detected by a satellite that looks at ocean surface elevation and ocean waves. It traveled more than 3,000 miles at about 300 miles per hour, killing 300,000 people in 11 countries. Huge, huge tsunami. We know better now. There is now tsunami warning systems in the Indian Ocean. Here we can see a coastal city. Lots of buildings. There's the town mosque right in the center. Lots of green. A year later, completely stripped away. Buildings are gone. Vegetation is gone. Everything is gone. Because the energy, right? If we think about how much energy waves transmit, a tsunami is that to the nth degree. So much energy in these tsunamis. Japan's earthquake was also devastating. Topped the harbor protecting tsunami walls. Japan knows, right? Tsunami is a Japanese word, and Japan is familiar with large tsunamis, and so they actually have tsunami seawalls that protect their coastal cities. But this earthquake was so big that it topped over them. Whoa, okay. How powerful can the ocean be? We can't even dream it. We can't even plan for it. But maybe we're starting to get an idea because our understanding of oceanography is increasing, and we've also had these global tragedies happen. They're fresh in our minds. It's a shocking image showing the boat is picked up, put on a building. Everything else is basically gone. And this is for many, many coastal towns. Tsunamis affect coastal communities. The wall of water can be 50 to 120 feet high, and maybe even bigger if we have an even bigger earthquake. So what do? We can develop these tsunami warning systems. In Hawaii, we have the PTWC, the Pacific Tsunami Warning Center, that collects information from the Deep Ocean Assessment and Reporting of Tsunami DART. Basically, it's a bunch of buoys out in the middle of the ocean that measure the height of waves passing through, and they can record if there's big waves. There's a tsunami. We feel the earthquake. These buoys measure increased wavelengths. We can let people in coastal communities know who have tsunami preparedness, evacuation drills, and we can protect and minimize the loss of life from these big events. So the buoy is attached to the ground. It floats on the surface. It communicates to a satellite. That satellite goes to the research center, and then we can issue tsunami warnings and help to, and hopefully never have a disaster that kills 300,000 people. Oh my gosh. Let's be prepared. Let's be proactive. Let's monitor. Let's assess. We know these things happen. Let's protect the value of human life. Not only that, let's use these waves to support us, because I haven't said climate change once today. Amazing. But climate change is a thing, and divesting from fossil fuels is ultimately important, and investing in alternative forms of energy like wave energy. Now, there's environmental issues. There's two types of wave energy. You can build a station on a coast, and as the waves come in, it compresses the air and shoots it through a turbine. Or you can have waves out off the coast in a wave farm. And waves off the coast in a wave farm, and then as the waves move through, they create energy and transmit it down into underwater cables. With any type of infrastructure that generates electricity, there will be environmental effects. And so looking at, is this a viable source of energy? Can we create enough energy to make it worthwhile? And one thing about wave farms is you need waves. So strategically locating wave farms in areas of increased wave energy resources is a proactive way. And where do we see that? In the subtropics, where the westerlies are, in the northern and the southern hemisphere, and then associated with coastlines, where the wavelengths decrease, the wave heights increase, the wave energy starts to dissipate, and that can be collected, transferred, stored, and utilized for electricity. So, wow, okay, waves, the full spectrum, the components of a wave, the characteristics of waves, how waves are generated, what types of waves there are, what happens when they come to the coastlines, and tsunamis, wave energy generation. So that was awesome. I hope you learned a lot about waves. If this is new information, definitely dive in a little bit deeper to anything that you might need to review again. And yeah. Oh, and surfing waves, of course. So let's go surf some waves. Thank you everyone for your attention. Great job today, and I'll see you in the next one.